Okay, today we're going to start a new chapter. Okay, it's called reversible reaction. Okay, what is a reversible reaction? Okay, a reverse. Okay, so it's called reversible reaction. Okay, now reversible reaction means like this. It's the chemical reaction shown by this. Okay, so a reversible reaction means that the reactant becomes the product, right? The product can change back to the reactant again. Okay, so I explained to you a reversible reaction. Okay, a simple reversible reaction, for example, okay, let's say I take hydrogen molecules, okay, and I react with iodine molecules, okay. So the hydrogen and iodine bonds break, need to break bonds first, right? And then they form hydrogen iodide. Now, let's say I start with 50, okay. After 25 and 25 of this is used, how many of this will I get? 50, okay. It looks like it's balanced, right? So what happens is the hydrogen iodide not very happy, so they split up again and become this. So that's called reversible. Okay, so maybe, okay, so this reaction, when we write it down, we write the equation like this. The arrow is like this. So this is called a reversible arrow, reversible reaction. Okay, so hydrogen and iodine are the reactants. Hydrogen iodide is the product. But then the product can change back to the reactant again. So the reaction that's going, okay, why am I lying like that? The reaction that's going this, I have to stand, I have to arrange it. Okay. The reaction that's going this way, we call this the forward reaction. Okay, we call this the forward reaction, or we call it the reaction to the right. So shifting it to the right. Okay, and then the other way, if it goes this way, can you all write this down? It is called the reverse reaction or backward reaction. Or we say it's going to the left. Okay, now these two, because they're in front, they are still called the reactant. They are still called the reactant. This one, because it's at the back, we still call it the product. Okay, but the reaction can go both ways, where the reactant can change to product and then the product can change to reactant. Okay, how was your concert? How was your concert? Yeah, can you understand? Now, do you all remember endothermic and exothermic? Okay, so if the forward reaction is endothermic, if the forward reaction is endothermic, then the reverse reaction will be exothermic. But if the forward reaction is exothermic, then the reverse reaction is endothermic. Okay, so it depends. Okay, now example, in a reaction, do you think you will want more product or want more reactant? In any reaction, you want more product or more reactant? To, of course, product lah. Who's so stupid put the two things together? You want to make, you want to make, never mind. Where got such thing, right? Of course, everybody wants lots and lots of product. So having lots, the amount of product you get is called yield. This word yield. Yield means how much product you get. So people want higher yield or lower yield in any. So this one we're going to talk about. We're going to talk about what do you call it? Industrial reactions. Okay. All right. So industrial reactions, of course, you want a lot of yield. You want a lot of product. Can you understand? Okay. Now, one example of a reversible reaction, two that you need to kind of remember also lah. It is copper 2 sulfate and cobalt 2 chloride. Okay. Copper 2 sulfate and cobalt 2 chloride. These are also used to test the presence of water. Okay, now when we start out the experiment, if there is water, if you cannot call something got water and no water. You cannot call it that. You call it anhydrous or hydrated. Anhydrous means got water or no water. Anhydrous, no water. So when you write the no water, it's just like that. CuSO4. COCl2. So this is called anhydrous copper 2 sulfate. This one is anhydrous copper 2 sulfate, and the other one is anhydrous cobalt 2 chloride. You need to remember the color. You need to remember the color. So anhydrous copper 2 sulfate is white. When you react with water. So hydrated, it looks like this. The formula looks like this. CuSO4 dot 5H2O. So when it's hydrated, it's crystals. Okay, 2,000 points for the person who tells me what is the color of crystals copper 2 sulfate? Blue. Blue, remember? Copper 2 sulfate is blue. Okay, so you take the anhydrous copper 2 sulfate is white color. You add water, it will turn blue. That's how you prove the thing that you're adding is water. It doesn't test for the purity of water. Purity is how? This one is just to test the presence of water. That means got water or no water. If I take alcohol and I drop alcohol, will it change color? No. If I take oil and drop, will it change color? No. Only change color with water. If it's salt water, will it change color? Yes. If it's tap water, will it change color? Yes. If it's sweat, will it change color? Yes. The sweat also got water. Okay. Any water, longan water also it will change color. It's just proving there is water. But if I want to prove that it is pure water, what do I do? Testing the purity of water is what? You want to test whether it's pure, what do you do? Test for? No. I want to prove this water is pure. You test the what? Boiling? Boiling point must be exactly 100 degrees Celsius. Or you test melting point. A pure substance, pure water, will boil at exactly 100 degrees Celsius. So this is a very common question. They ask you to prove to me it is pure water. It's a different answer. They ask you to prove to me that it is got water, presence of water is two different questions. Okay? So prove to me that this is water. Then use anhydrous copper 2 sulfate. It's white, it will turn blue. Prove to me that this is pure water. The boiling point is 100 degrees Celsius. Okay? Cobalt chloride is terbalik. The anhydrous cobalt chloride is blue. When it becomes hydrated, cobalt is CO. It will turn pink. Okay, so this one is we use it as cobalt chloride paper. sorry, this is 6, not 5. 5 is for copper sulfate. Cobalt chloride is 6. Is that 6? This one 6. Okay, so blue to pink, pink to blue. But is the reaction reversible? Yes, the reaction is reversible. Meaning that if I take, so that's why when we write this equation, we can actually write it with a reversible reaction. Because I can heat it up and it can change back. Can you understand? So if I take blue hydrated copper 2 sulfate, I heat it up, eventually it will turn back to become white. If I heat up pink cobalt chloride paper or crystals, it will turn back to become blue. Make sense? Okay, so this is a reversible reaction. Another reversible reaction is like melting lah. Melting. Okay, so if I have ice to become water, can water change back to become ice? Of course. Ice change to become water, absorb heat or release heat? Absorb. So absorb is endo or exothermic? Endo. So water become ice is release, and this is exothermic. Get it? So if forward is endo, reverse is exo. It's always like that. I'll scroll up. Oh, sorry. Up some more. Okay. Okay. Okay, ready? Can I continue? Okay. So, now I'm going to show you what equilibrium means. Okay, right. When I first start an experiment, okay, equilibrium must be in a closed system. Okay, a closed system can be equilibrium. Have you heard what equilibrium means? Equilibrium doesn't have to be same. Equilibrium means no more changes. It doesn't have to be same. Okay, it's not 50%, 50%. It could be 70% and 30%, but that 70% and 30% stays at 70%, 30%. It doesn't change. So equilibrium doesn't mean equal. It's not the same. Okay? So like this. When I have a closed system, let's say I have 5 hydrogen molecules and I have 5 iodine molecules like just now. Okay, what's happening is maybe it will change and become okay, maybe I use even numbers because it's 2 to 1. Okay, let's say I start out with 10 hydrogen, 10 iodine. So let's say 5 of it react. So I'm left with 5 of this, and I have 10 of this. Okay, now it might not stay the same. The 10 of it will split again to form, let's say it becomes 8 hydrogen iodide. That means how much hydrogen and how much iodine do I have? Hmm? 6 and 6. Okay, now 866 is not the same, but let's say after 20 minutes it stays at this. That means every time 1 hydrogen and 1 iodine combine to form 1 hydrogen iodide, it split back to become. So it goes back and forward. There's no more changes. So this is not changing anymore. So this one is, let's say, 0 minutes, and then this one is 5 minutes. It's like this. And then at 20 minutes like this, after 1 hour, it's still the same. Okay, so is there no reaction or got reaction? It's just that when one go here, another one will come back. When one go here, one will come back. That is called equilibrium. So we say that the rate of the forward reaction is equal to the rate of the reverse reaction, and the concentrations of the reactants and the products are no longer changing. So this is your definition of equilibrium. So can you please write this down when they ask you what is equilibrium? So what is equilibrium? Okay. Equilibrium is when the rate of the forward reaction is equal to the rate of the reverse reaction and the concentrations no longer change. Okay? Can you please write this down? This part, the one that I circle and tick it. Okay? Can you do that? That's the definition. They always ask the same question. So even if I leave it there for 2 hours, 3 hours, it will still be the same. Okay, it will only change if there's a hole in the system. That means it's not closed anymore. I left it open. If I didn't, have you seen a, what do you call that? What do you call that? A biosphere before, where they put a glass jar, they put, what's it called? Terrarium, but it's not closed. It's not open, it's closed. Is the terrarium closed or is it open? Closed. Okay. You don't need to plant anything. You don't need to remove the plants. You don't need to add water. It will stay like that forever because the plant uses the carbon dioxide for photosynthesis. It will release the same amount of carbon dioxide. They absorb the water for photosynthesis. They release the water during transpiration. It just goes on and on and on. They will never die. Get it? Do you know what I want you to copy? Okay, why are you staring at me like that? Are you okay, my dear? So you understand? Can understand? Get the idea? Okay, now predict and explain the reversible reaction, how the equilibrium can be affected. That means now this one is happy already. It's at equilibrium. That means at 866 it's happy already. It's not going to simply change. If it changes, it will change back. If it changes, it will change back. But it's happy already. How can you change it though? You can change it by changing the external factors. That means you can change the temperature, pressure. Look at this. Changing the equilibrium, you change the temperature, pressure, concentration catalyst. Doesn't this look very familiar? This is equilibrium. Everybody understand what's equilibrium? So how can you change the equilibrium? Is by changing temperature, pressure, concentration catalyst. But then, that day we talked about rate. Changing rate, how to change? Is it temperature also? Macam sama saja. Also temperature, and then is it also pressure? Yeah. Is it also concentration? Is it also catalyst? What's one more that's not here? Rate got 5. Temperature, pressure, concentration, catalyst, one more. Particle size, or otherwise known as surface area. Okay? Temperature higher, rate higher. Pressure higher, rate very easy. Temperature higher is faster. Pressure higher is faster. Concentration higher is faster. God catalyst is higher. The particle size is smaller, is faster. Very easy. This one, it depends. Okay, so how rate is how fast. Yield, equilibrium is yield. Yield is how much. It's two different things, two different concepts. Yield is how much you get. Rate is how fast you get it. Okay, for example, I have a factory. What do you feel like making today? What's your favorite thing that you feel like making? Children. What got? Cookies. Okay, let's talk about cookies or brownies. Oh, you're so weird. Okay, brownies. There's a shop in SS2 that sells small brownies with marshmallows on top. Yeah. Okay, my factory makes brownie. Okay, if I make 5,000 brownies per day. Okay, 5,000 brownies per day. The other one makes 60,000 brownies per year. Okay, this one is low yield, got very little but fast, so high rate. Get it? This one is high yield, a lot, but low rate, very slow. Can you see it? Can you see the difference? Okay, so this one is 5,000, so little only, but in one day. Okay, this one is 60,000, oh, a lot, but you have to wait 1 year. Okay, so if you are a factory and you are selling brownies, which one you want? 5,000 per day or 60,000 per year? 5,000 per day. But what if I change it to 500 per day? Also not that good, right? You know, depends if you work every day. So, what do you think the factory will want? High yield, the factory wants a lot of yield or a lot of rate? Which one? Or do they want both? Both. They want both. Okay. Now, this one we talked about already. This one we talked about already. High temperature, high rate. High pressure, high rate. High concentration, high rate. High catalyst, high rate. Particle size small, high rate. We already talked about this. But this one depends. Okay. So what I want you to write down is, I want you to write down this. Factors affecting yield is this 4. Factors affecting rate is this 5. Okay, can you write this down? So the yield is known as the where the equilibrium is known as the yield. So factors affecting the yield is this one: 1, 2, 3, 4. Factors affecting rate is this one: 1, 2, 3, 4, 5. And this one you already know. High temperature, high rate. High pressure, high rate. High concentration, high rate. That is the catalyst, high rate. Particle size is small. The rate is high. Okay, write this down. The yield will only affect a reversible reaction. Can you all understand? It will only affect a reversible reaction. So let's say the reaction is non-reversible. So if you change it, you won't affect the yield. You only affect the rate. Okay? Okay. Are you done? You done already? Say now. Waiting for you. Okay. 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 What is Haber process? You should have the poster of this person, Mr. Fritz Haber, instead of your Taylor Swift in your home. Why? Or your Blackpink in your home. Because without Mr. Haber, we will all be very, very hungry. Mr. Haber invented this process called, what did he call? Haber process. Okay, Mr. Haber invented this process called Haber process. It is not he invented ammonia. No, he invented how to make ammonia very, very fast. Why is it important to make ammonia very, very fast? Because ammonia is used to make what? Exam? Ammonia is used to make what? Fertilizer. Okay, ammonia is used to make fertilizer. And fertilizer is used to make sure you have many, many what? Plants. Okay, so all our vegetables, no matter you want to be organic or not organic or whatever lah, all our the ability to feed 6 billion people in the world is because I think many billion? What's our number now? 8 billion. 8 billion people in the world is the real achievement of fertilizer. Is it good or bad? No, I don't know. Because most of the food we plant used to feed animals, not feed human. So if all the food we plant is used to feed human, then we have no more world hunger. Okay. So ammonia is used to make. First thing I want you to write down is please write down the big word Haber process in your notes. Write down the word Haber process. Okay. It is to production of ammonia. And then ammonia. Ammonia is used to make a lot of things. But the most important thing it is used to make is fertilizer. Okay. The most important thing it's used to make is fertilizers. Okay, so all right, now first you must know where everything comes from. So where does nitrogen come from? Nitrogen comes from the air because the air is 78% nitrogen. Okay, this equation for Haber process, you kind of need to memorize it. It's going to be your best friend for the rest of the year. Okay, so it's just from the air. The hydrogen comes from methane. Methane is CH4. So you break down methane, not break down lah. You react methane with steam, you get hydrogen. Okay, so this is how you get these two gases. So what happens is we're going to talk about it one by one. We're going to talk about it one by one. Okay. Okay, you need to write down this equation. Okay, you need to write down this equation. Okay, we're going to talk about this equation a lot. Okay. Okay. Okay, guys, look here. Yeah. Now, can you see that this is gas and gas and gas? Okay. How many moles of gas do you have here? How many moles do you have here? This one, wait, how many? How many moles of gas? How many gas do you have here? How many moles? 1. Here, how many? Here, how many? 3. Very good. You can recognize numbers. Yay! So total is 4 moles. See, I didn't even try you with arithmetic. I told you 4 moles. All right. Over here got how many? At the product got how many? 2 mole, 2 mole. Okay. Now, if the pressure is high, now listen first. If the pressure is high, remember, equilibrium only affects a closed system. So all the molecules are here. All the molecules are here. If you increase the pressure, increasing the pressure means you squash it and force them to take a smaller volume. You increase, you push the pressure. Do you think they will try and make more moles, which take up more space, or try and make less moles that take up less space? Less. Understand? So, who has less? The reactant or the product? Product. So, please write this down. High pressure favors the side with less moles. Always remember this. And this is only of gas, only gas, but 99% of the questions that they will ask you is all about gas. High pressure, please write this down, favors the side with less moles. So when you put high pressure, will it move to the front or forward or move to the Forward or backward? It will favor forward or favor backward? Huh? Forward is it? It will, now I put high pressure. Here got 4, here got 2. It will favor the side with less moles. So who got less? Forward lah. Okay, so more, okay, better word, more yield or less yield? Huh? When you put high pressure, less moles is this way, right? So yield means product, right? So now more product or less product? The whole reaction favors this side. All of them favor this side. All get pushed here. That means they are making more of this. They are making more of this, huh? So they are making more product. So high yield or low yield? High yield lah. Is this the product? Am I making more of it? So high yield. Get it or not? It favors the side with less moles. Who has less moles? The reactant or the product? Product. Okay, wait, let's try another reaction. Okay. If like this, 5x, okay, x6 plus y become cannot. Okay, never mind. Okay, basically, don't bother about balancing. It forms xy. Let's say the ratio is 6 lah. Okay, pretend. Okay, let's pretend. Okay, look at this. This is the reactant, right? No such thing in the world. Okay, this is the reactant. How many moles? 2 moles. The product, how many moles? 6. Okay, so if I put high pressure, it will favor the side with less moles. Which side got less moles? The reactant or the product? Reactant. So high pressure will favor this side. Get it? So this is my product, right? So I will have more product or less product. It's going this way. The reaction is reversible. It's going this way. I'm going this way. So I will make more of the 2 or I'll make more of the 6. 2. So this one less or more? Less product. So low yield. Get it? Okay. This is only pressure. Now, if my reaction is like this. This is not reversible. We pretend it's reversible, okay? We just pretend. Okay. Shh. Here how many? All gas now, all gas. Here how many? 3. Here how many? Okay, I want, if I use high pressure, it will favor which side? Product. So high yield or low yield? High yield, higher lah. Get it? Okay. Last one. If I have this. Uncle, can you put down your phone? Okay. Here got how many? Here got how many? So if I put high pressure, is it going to affect anything? Get it? All right. Make sense? Make sense or not? Okay, so if in this reaction, in this reaction, this one, I want to increase the yield. I want to increase the yield. Should I use high pressure or low pressure? Very good, low pressure. Because low pressure will favor the side with more moles. Get it now? Okay. So let's go back to this. Okay. High pressure favors the side with less moles. Okay. How does high pressure affect the rate? High pressure, high rate or low rate? High rate. High pressure, high rate. Get it? So in this factory, if I use high pressure, I will have high yield. So high pressure, high yield, high pressure, high rate. Wait, let me write it down. So high pressure, high yield, high pressure, also high rate. So what do you think I will use? Will I use high pressure? Yes, because it fits both the categories. So in Haber process, in order to make this very, very fast, we use the pressure 200 atmosphere. Do you need to memorize this? Of course, you need to memorize this 200 atmosphere. Okay, I have okay. ATM is atmosphere, yeah. All right. Now, listen carefully. Listen carefully, yeah. Okay. 200 atmosphere gives me high rate, also gives me high yield. I'm very happy. Why don't I use 300 atmosphere? Why don't I use the pressure of 300? Better kan? Lagi better. Why I stick with 200? Why not higher than that? Hard to control is dangerous. It might explode. Okay, it's dangerous. It might explode. It's also expensive. So we don't go beyond 200. Understand? Okay, that's part one. Part one here. Okay, so remember, pressure favors the side with less moles. Okay, have you written this down? So we finished talking about pressure. All right, now we're going to talk about the second one. Huh? We finished talking about pressure. Now we talk about the second one. Kelly, I already said stop saying that. Okay, ready? Nana, can I continue? Okay. So let's do part two of this. So we talked about, now we talk about pressure. Okay. Now we talk about temperature. high temperature. Okay, the forward. If I tell you, this forward reaction is exothermic. Okay, the reverse reaction will be what? Exo-endo, endothermic. It's always like that. Okay, going this way is exothermic. Going this way will be endothermic. All right. Now, high temperature okay, high temperature favors the side, the endothermic reaction. Why endothermic? Okay, you think of it logically. Endothermic means I absorb heat. Okay, endothermic means I absorb heat. So when I give you heat, will you release heat or absorb heat? Absorb lah. So I give this system more heat. I give this system more heat. What is it going to do? Is it going to, oh, I give you heat. Okay, like for example, I give you a lot of food. What are you going to do? Take out some more food or you're going to eat the food? This is in my house. I take out food and I see I take out food and I say, come, let's eat. So what's the logical thing? Oh, there's so much food on the table, come, let's eat. Is it logical? There's so much food on the table, come, let's go and buy some more food. That doesn't make sense. Normal people, that doesn't make sense. Okay? So what happens is on the table has a buffet, all the food you ever want to eat. So of course you will sit down and eat first lah. If there's no food, then only you go and buy food. Right? So now endothermic is absorb heat. So if I put more heat, which way will it go? The direction that absorbs heat or the direction that releases heat? Absorb heat. So if I put low, so high temperature favors this side. Low temperature favors this side. So if I want a lot of product, if I want a lot of product, should I use high temperature or low temperature? I want a lot of product. Low temperature. So low temperature, high yield. For this reaction, because the forward is exothermic. Okay? So, but low temperature, high rate or low rate? Low rate. How like that? If I use low temperature, I get a lot. I get 5,000. I get 60,000. Very slow. If I use high temperature, I get 5,000. Only 5,000, but very fast. So we compromise. Okay, so in the table, what he figured out is you must compromise. Okay, so you compromise. Okay, so you use, I got no place to write compromise. You use 450 degrees Celsius, so that the rate is high and the yield is okay. Okay, the rate is high and the yield is okay. So the question that have you written this down? You write this down because then I'm going to tell you about a question that they always ask. Yes, it's the same question. It's just that just now we were talking about pressure, now we're talking about temperature. Okay? Yes, this is still under Haber process. Haven't finished yet. Haber is a very long thing. Okay? Ready? All right. Now, let's go down. Oh, sorry. Okay, so the question that they always ask is, why not 600 degrees Celsius? Yeah, the rate will be higher, but yield too low. So you compromise. You use 450. So just now, Haber process, the pressure is 200, right? The temperature is 450. Okay? Okay? Okay, now, see, if x plus y become xy, and this reaction is endothermic, I use high temperature. Will I get high rate or not? Do I get high rate? I use high temperature, do I get high rate? Yes, because rate is not affected by any equilibrium. High temperature, high rate. Okay, this one reversible. Reversible. Okay. So if I do high temperature, I get high rate. Do I also get high yield? Yes or no? Do I get also high yield? Yes. Because high temperature favors endothermic. That means this direction is endo. Can you understand? Okay, I'm going to only end with one last thing, which is catalyst is iron. For Haber process, catalyst is iron. That one is fixed. Okay, iron makes it high yield, also make it high rate. Actually, it just increases the rate that it reaches equilibrium. Okay, Haber process not finish. Still got some more. So, but it's not very hard. This is the main part. So the three things that we use for Haber process is 450 degrees Celsius, 200 atmosphere, and iron catalyst. This one is 3 marks already in exam. 250, 200, iron. They ask you what are the conditions for Haber process. Yeah, but you get the yield higher. You will just reach the equilibrium faster. So it makes the whole thing faster. So that's why, okay, how can I use this to increase surface area? How can I increase surface area? So what we do is we do this, okay? So we put it in a vat. We put this all in a vat. But what happens is here, the iron is iron beds. So we increase the surface area. So here is the mixture of all the gases, the nitrogen and the hydrogen mixed together. But here is the iron catalyst is like that. So increases the surface area. Okay, so that the gases will be exposed to more iron. Can? Okay, we continue.